Well, good morning, team. You ready to get into some nitty gritty for how we're going to focus on metallic substances, right? So, iron, copper, tungsten, whatever. And we looked at the different types of unit cells for cubic structures, right? So we looked at face-centered cubic, body-centered cubic, and simple cubic. So let's take a look. We're going to see a little overlap with this and then introduce a new one, looking at how these atoms actually stack. Like I use that example, if you go to the grocery store and you see, spherical oranges, we're treating atoms as spheres, right? Treating atoms as little spheres, like marbles in a box or something, and how you can take these oranges and start stacking them. And you see these little pyramids form, okay? So we're going to look at that and call this what's called closest packed structures. We want to get, and it's just this one type, right? We want to get those spheres, those atoms, in as close of contact as possible, right? So we want to maximize the space within a unit cell that the atoms encompass, and we want to minimize the space between them, the void or the holes between them. We want to minimize that space. We want to pack them in as best as we can, and there's very specific ways to do that. That would create like maximum density possibilities, right? More atoms in there. So the volume of the open space, some people call those voids, right? We want to keep that to a minimum. This is going to give us two types of structures based on the closest packed. So the other ones we talked about would not be considered closest packed. They might be close to the closest packed, but not quite as efficiently stacked. So let's take a look at how these two possible structures come into play based on how we stack layers of atoms. So we're going to do a layer of atoms, then a second layer of atoms, then a third layer of atoms, and place them in there and pack them in as tightly as we can. Get your geometry hats on again. Let's take a look at how these babies stack. The first layer is by far the easiest. It gets more exponentially harder to see. This is when you keep adding layers to it. This is really hard to do in a large lecture hall. If I'm teaching a class of 140 or something, I'm like, can everybody see this? And I can put things up on PowerPoint overviews or do little video turns or whatever. But you need to have a model set. So these are 3D printed model sets. We got a 3D printer in our lab, which is kind of fun. But and I set these up in my labs where, if you're standing in line to wait to ask a question, you can play around with these and stack them and look through them and go, I see it now. First layer, pretty easy, right? So imagine you've got some central atom, so this shaded one right here. So pick any one of these as a central atom, say this one. We're going to surround it by 1, 2, 3, 4, 5, 6 other atoms, like a hexagon. You see that hexagon there? So looks like so, Yahoo. So I got the hexagon around it. But that creates little spaces. Do you see all those little spaces formed by 3 atoms? Looks like a little triangle. Does that look like a triangle to you? Oh, so we can name this particular hole, right? So we can name this particular hole. That is called a trigonal hole. Big surprise. So whoops, I lost that. So right there is called a trigonal hole. Looks like a triangle formed by 3 atoms. So we're in this, like a one-dimensional layer. Now we take the next layer, there's really no option for it to go. Here's the next layer, right? It has to go in those trigonal holes, right? There's no other option for it. It has to go in the trigonal holes, no matter what color you use. And it's going to be a different type of layer. So if I place these in the trigonal hole, right, now you can see through. I'm going to do this on the next board. But would it make sense to you that the next layer has to go? So you're going to take an atom and it's going to nestle in this little dimple between these 3. Right, so it's going to nestle right in there. It sits perfectly when you're stacking oranges. That's where the next orange goes. Boop! Right, so let me draw that on the next board. Boom! The second layer goes into the trigonal holes. Let's write this down. So the second layer of atoms has no option, right? It must go into the trigonal holes in layer number 1. We like that. It's like going to a restaurant and you go to order and there's one thing on the menu. I guess I'll take that. It releases a lot of stress from your life instead of like 52 options. I don't know what I want. So let me give it a shot. I'm gonna make this a little bigger and I'm gonna put the second layer in those trigonal holes. And it's hard to see on a two-dimensional board. It'll be easier to see with the models, and I'll zoom in so you can see what I'm talking about. Layer number 2 was really, that took me forever. So it takes 2 seconds with a model and 10 minutes to draw on the board. Iteration number 6. All right, so we looked at that first layer and we saw that the second layer has to go into the trigonal holes in layer number 1. No option, right? No option whatsoever. So layer number 1, trigonal holes, boop. Layer number 2 goes into the trigonal holes. We'll do the layer 2 in blue. I should have done that in blue. Here I did layer number 1 in red like this, but I did the second layer in brown. Wasn't thinking I should have done blue, right? This creates 2 new hole types in layer number 2. So let's take a look, and then we'll see how it is on the board. So based on where it stacks, now look through. Okay, can you see through that hole there, right? See those 3 atoms? You can see the red atom in layer number 1. But in the one next to it, we're overlooking that trigonal hole in layer number 1. You can see the difference, right? And they alternate. So there's that, overlooking an atom in layer 1, overlooking a hole in layer 1, overlooking an atom in layer 1, overlooking a hole, overlooking an atom, overlooking a hole. You can see the 2 different types of holes. So the next layer could go in those holes, right? Overlooking the first stack, repeating the first stack, or they can go in these holes, which would form a completely new stack. So it gives you 2 different types of structures. So the 2 structures have the same first and second layers. It's just the third layer can go into one of those 2 different types of holes. There's names for those holes, right? So the first one that's overlooking an atom in layer number 1, whoop, right there. So that's formed by 1, 2, 3 blue ones and a red one. It's formed by 4 atoms. So it's called the tetrahedral hole, right? So if I put the third layer in the tetrahedral holes, it gives me one type of closest packed crystal structure, right? You can see the reds there. Those are tetrahedral holes. You're overlooking an atom in layer number 1, okay? Formed by 4 atoms. But if you take one where you're overlooking a hole in layer number 1 right there, well, that's formed by 3 atoms in the top and then the 3 reds in the bottom. So that's formed by 6 atoms. That's called an octahedral hole. Right? Looks like an octahedron. So that looks through the holes in layer number 1. So there, and there. Those are octahedral holes formed by 6 atoms. So if the third layer goes into the octahedral holes, we get a different type of closest packed structure. Ha 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 ha. Good luck doing that, right? So I will do that on the next board. Right? And again, good luck trying to draw that on a 2-dimensional surface. It's insane. So what I'm going to do when I draw it on the board, instead of drawing it from the top view, I'm going to draw it from the side view where you'll see if it goes into a tetrahedral hole, you'll repeat the first layer. So it'll go red, blue, red, or something like that. Or I could go blue, red, blue, right? Depending how you do it. If it goes into an octahedral hole, you get a whole different type of layer that doesn't repeat layers 1 or 2. You get a third distinct type of layer. Let's take a look at that. Ready for some weirdness? All right, here we go. So we've got the first layer. I made it blue this time. Second layer red. And if you look through, you've got the tetrahedral holes and octahedral holes. If the next layer goes in the tetrahedral holes, it repeats the first layer, right? So I'm going to pop these right in that tetrahedral hole. Let's line it up so it looks exactly the same. Boop. It repeats the first layer. You see that? It's like a sandwich. Okay. So here's the side view. So if I did that first layer in blue, the second layer goes in the trigonal holes, that'd be red. And then the third layer goes in the tetrahedral holes, that repeats the first layer. Let's call the first layer A, the blue one. The second layer B, red. Well, the third layer is exactly the same as first layer, so we could just call that A again. And then you repeat yourself. And then the fourth layer, you've now got these trigonal holes, right? So pulp, it repeats layer B. So you get this A, B, A, B, A, B, A, B repeating structure. Blue, red, blue, red, blue, red, blue, red. So that type of arrangement, oh, I lost my second layer, right? This is called hexagonal. Some people call it hexagonal. Some people call it hexagonal. I don't really care, right? Hexagonal closest packed structure, or just HCP. Whenever you see that CP, you know it comes from this closest packing arrangement, okay? And I'm going to, on the next board, talk about this hexagonal closest pack arrangement. This is not what we've seen. This is not one of those, face-centered cubic, body-centered cubic, simple cubic. It doesn't have this beautiful cube unit cell. It actually has, I think it's a parallel pipette or something, more like a diamond shape. So let's talk about, its coordination number and the number of atoms in there. But we're not going to calculate the volumes of HCP structures in terms of length and radius and calculating densities like we will the other ones. It's a little more than I want to do, but let's take a look at what this is on the next board. All right, so for HCP structures, a little harder to see, so I tried to draw different views on the board for you. So this would be kind of a unit cell where you've got the atoms in the corners, like the simple cubic type thing, just like FCC, BCC, those kinds of things. And you have an entire atom. So this would be like layer 1, but the centers, then layer 2, and then layer 3. And if you look at those 3 layers, the ABA structure, that second layer falls in between, but one entire atom falls inside the unit cell, but it's not exactly in the center. So it's kind of like a BCC, body-centered cubic, but it's off-center in the middle. It's shifted a little bit. And so the unit cell is not like a cube, it's like a diamond shape, all right, the parallel pipette. If we just look down from the top, okay, look down from the top, you'll see that diamond shape of the unit cell, and then you'll see that center one through a little bit, and it's actually inside that cell. So because we know that, we can calculate the number of atoms inside the cell, just like we did for simple cubic, which was 1, body-centered cubic was 2, and face-centered cubic was 4. Well, you've got the corners, right? And you've got 8 of them times 1/8 would be 1 atom. Plus you've got that one off center in the middle that's entirely in there for a second one too. So that has 2 atoms total inside it. So an HCP has 2 atoms in the unit cell, just like a body-centered cubic. But they're shifted a little bit because that's off center. It has a different coordination number. Right? The body-centered cubic was right in the middle, touching the 4 above and 4 below, right, for a coordination number of 8. But this is a little bit different. So this, you can see, if you take so pick any one atom, right? So you take that atom. So this comes from the closest packing, right? Can you see you've got 1, 2, 3, 4, 5, 6 in the layer? So it's touching 6 in the same layer. Well, then you've got the layer above it that stacks on it, where you've got 3 touching that one atom, right? So you pop it in there, see how 3 of them are touching it? So you get 3 above, and then you have another layer where you've got 3 below. So you've got an atom with 6 around it, right? You've got an atom with 6 around it. You've got 3 nestled above it, and 3 nestled below it, for a total of 6 plus 3 plus 3 is 12. Has a coordination a number of 12, just like the face-centered cubic. All right? And if you take 3 from like the top view, 3 of these unit cells, so I'll do 1 in red, 1 in brown, 1 in green, put them together. Do you see the 1, 2, 3, 4, 5, 6 sides? Right? 1, 2, 3, 4, 5, 6. So it forms this kind of a hexagonal shape overall. Kind of cool, right? Hexagonal closest pack. And again, we're not going to do the volume of the unit cell related to atomic radius and edge lengths and things like that, like we did for face-centered cubic, body-centered cubic, and simple cubic. All right, so that's the first type of closest pack structure, the hexagonal closest pack structure, AB, 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 AB. Now let's look at the situation where that third layer goes into the octahedral holes and forms a complete new layer C. So you get the ABC structure. Let's do the second option now. So we've got layer number 1. Whoa, almost dropped it. Don't drop the layer number 1. Trigonal holes. Layer number 2 goes into those trigonal holes. Wada bing, wada boom. Gives you your tetrahedral and octahedral holes. Now the last one, the hexagonal closest packed HCP, went into the the tetrahedral holes, right? Now we want to go into the octahedral holes, and that's going to create a whole different structure. Oops, wrong holes. Boop. That creates a third structure. You see that? So let's call that first layer A, second layer B. I don't have green ones, so we'll make the white one C. So we get this ABC, and then the next layer would repeat the first layer. So you get this ABC, 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 ABC structure repeating. That's a totally different structure than what we had before. Remember, the hexagonal closest pack was AB, 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 so you repeat it. This one, you get 3 separate layers, ABC, 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 as you stack it up. That is called a cubic closest pack structure, or CCP. Very different from the hexagonal closest pack. They're both closest packed. They're going to have the same coordination number of 12. But that third layer is going into the octahedral holes, which overlooks the spaces in the first layer. Hey. Now, this I don't have the model to be able to do this. It's a shish kebab one, where if you take this cubic closest pack structure and you rotate it in a very specific way, you have to kind of, it doesn't work with this model set, but if you rotate it and you kind of hack off some of the atoms here in the end, you can actually see the face-centered cubic structure. So cubic closest packed gives you the face-centered cubic structure, right? So it's a different way of looking at face-centered cubic, where now we can look at face-centered cubic, which we know has a coordination number of 12, which I talked about before, but now we can see it as the closest packing, where you've got the 6 here, and then you'll have the 3 above and 3 below. So you have the coordination number of 12, just like HCP. But with the face-centered cubic, you actually get 4 atoms inside a unit cell rather than 2, like that HCP, hexagonal closest pack. Ooh, rock and roll. So I'm going to erase this board. I'm going to put up a summary of the 4 different types of crystals we've looked at: simple cubic, body-centered cubic, which are not the closest packed to there. Body-centered cubic is close. Hexagonal closest packed and face-centered cubic, or cubic closest packed. Let's summarize the coordination numbers, number of atoms, stuff like that real quick. Time for a quick summary table, and then we'll talk about one more thing, and we'll be done with the closest packed structures. All right, so here's our summary table. We talked about simple cubic, body-centered cubic, face-centered cubic, which we know now is cubic closest packed, going into those octahedral holes, and then hexagonal closest packed, going into the tetrahedral holes. All right, coordination number, if we remember when we talked about that in the last video, was 6 for simple cubic, 8 for body-centered cubic, right? 12 for both face-centered cubic and hexagonal closest pack. Because of the closest pack structure, they're smashed in as close as they possibly can, so they have the highest coordination number. BCC is not quite closest packed, but it's not too far off, so it's got an 8. Simple cubic, not so efficient, right? We calculated, I showed you how to calculate the number of unit cells. Each corner atom counts as 1/8 inside the cell. Each face counts as a half, and anything in the body counts as 1. That was both for the HCP and BCC, so those are the same. So a total of 1 for the simple cubic, just in the corners. Total of 2 for the body-centered cubic and the HCP, where you got the corners and that 1 in the middle. Body-centered cubic in the very middle. Hexagonal closest pack a little off-center. And then the face-centered cubic, or cubic closest packed, was the most smashed in there with a total of 4, because you had the 8 corners and then the 6 sides. We have not talked about the percent volume occupied, because that unit cell is not completely filled with atoms. It's atoms with space. It's got those holes, right? So I don't do this very much, but you can. You can actually calculate the percent volume occupied by atoms, or in the opposite vein of that, the percent of that unit cell that's actually empty space, right? And the more packed in you are, the less empty space you have. I'll show you how to calculate these on the next board. But 52%, only 52% of a simple cubic is actually occupied by atoms. Subtract that from 100, so 48% would be empty space. Woo! Wow, that's not super efficient, is it? 68% for body-centered cubic, and then 74% both for cubic closest pack, or FCC, and hexagonal closest pack. 74. That's about the max you're going to get right there. And we calculated these before using the Pythagorean theorem, right? So if you relate the edge length to the atomic radius for simple cubic, the edge length was just 2 times the atomic radius, right? For body-centered cubic, the edge length was 4 times the atomic radius over the square root of 3. That was the net result. Review the last video if you need to. And then for face-centered cubic or cubic closest packed, the edge length was the atomic radius times the square root of 8. We derived all those, body-centered cubic being the hardest one to do. So all you have to do to get the volume of the unit cell, because these are cubic, is just cube. It's just all the edge lengths are the same, so length times width times height, which are all the same, it's just length cubed. If you know the radius, just cube those and you're off to the races. The volume of the unit cell is good. We're not going to do that for the hexagonal closest pack because it's not so pretty. So let's end this. Let's talk about where these numbers come from. And it's the same regardless of what metallic atom you put in there, right? So I'm going to show you how the radius actually cancels out, and it's just based on some constants. Pretty easy. All right, this mystical percent volume of a unit cell occupied by actual atoms, right? So to determine that, well, just think, seems pretty straightforward. Take the ratio of the volume of the atoms over the volume of the entire cell. Times that by 100 to go from a ratio to a percentage, right? So take the volume, so the percent volume occupies just the volume of the atoms in the cell. We're going to make the assumption that atoms are spheres, okay, divided by the volume of the cell. Times that by 100. Okay, well, what would be the volume of the atoms be? Well, it's the number of atoms, which, well, I guess 1 for simple cubic, 2 for body-centered cubic, and 4 for the face-centered cubic, right? And 2 for the hexagonal closest pack. So take the number of atoms times the volume of the sphere, right? 4/3 pi r cubed. Well, that's pretty straightforward. And then we're going to divide by the volume of the cell. Well, we're going to be doing cubic cells only, so that's just the length cubed. We're not going to do hexagonal closest packed, even though we could. All right, and then times that by 100. So it depends if it's FCC, BCP, those kinds of things. So let's set it up for the 3 main ones and show you how those numbers come into play real quick, but pretty straightforward to set up. You ready to put some simple numbers to it? Let's take simple cubic. Let's calculate the percent volume, all right? So that's going to be the volume of the spheres, which is the number of atoms, times the volume of the sphere. So 1 atom times the volume of the sphere, 4/3 pi r cubed, divided by the length cubed. Well, the length is just 2 times the radius, so if you cube that. Now see how you're going to get r cubed here? You'll get 8r cubed on the bottom, and you've got r cubed on the top. So the r cubed cancel. So the radius is gone. So it's just 4/3 pi over 8. Right? Times that by 100, I approximated just to the nearest ones place there. It's about 52%. Let's do the same thing for body-centered cubic, where you have 2 atoms per unit cell times the 4/3 pi r cubed. So you get 8/3 times pi r cubed on the top. Well, remember, the edge length was 4 times the radius divided by the square root of 3, which we derived in the last video. Cube that whole thing. Well, you're going to get radius cubed on top, radius cubed on the bottom. So you're going to get 4 cubed over the square root of 3 cubed on the bottom, and then 8/3, 8/3 pi on the top. Just calculate those numbers out, times it by 100. I approximated to 2 sig figs, 68%-ish, right? And then for FCC, well, you've got 4 atoms in the unit cell, so 4 times 4/3 pi r cubed, volume of the sphere. And remember, the edge length for face-centered cubic was the atomic radius times the square root of 8, okay? And then cube that. You've got r cubed on top, r cubed on the bottom. So in every case, the radius cancels out. Sweet, right? So you get, the 4 times 4/3 pi on the top. You get the square root of 8 cubed on the bottom. Times that by 100, you get about 74%. We're not doing hexagonal closest packed, but you would have the 2 atoms. But we did not calculate how to get the volume of the unit cell. So we cannot do that calculation based on lacking information. We could do it, but I don't feel like it right now. All right, but you can see where those numbers come from. Now all you have to do is subtract that from 100. Right? So take 100 minus 74, that'd be the percent volume in the unit cell. That's empty space or void. 100 minus 68 for BCC, 100 minus 52 for simple cubic. Pretty straightforward to do. All right, that's it for closest packing. My end game is trying to get the densities, estimating densities or atomic radii from X-ray diffraction data. We'll do those in the next video.